Thank you very much, Melanie, for the kind introduction, and I would like to thank the organizers very much for giving me the opportunity to present at this very nice workshop. So I'll be talking about Wasserstein Distributionally robust optimization, and this is mainly joint work with Payman Mojari Nesfahani, who is at TU Delft, and with my two excellent PhD students, Viedan Nguyen and Sarouche Shafiezadeh. So in this talk, I would like to study some very basic stochastic optimization problems, where each decision corresponds to a loss function L of xi. And here, the random vector xi captures sort of all problem-dependent random variables and follows a distribution P. So I'm going to denote by script L here the set of all admissible loss functions, or admissible decisions in that sense. So I'm going to define the risk of a fixed loss function as the expected loss under the distribution P. And I'm going to define the optimal risk as the infimum of the risk over all admissible loss functions. So this is sort of an abstract way of formalizing one-stage stochastic programs. I sort of notationally suppress explicit variables for the decisions, and I just identify decisions with loss functions. And this is just to avoid clutter, so don't worry about that. These very fundamental problems, they have many applications already, for example, in news vendor problems, in portfolio optimization problems, but also in regression and classification. Of course, these kinds of problems also appear if you try to solve a dynamic program with value iteration, as an example. Now, a very fundamental problem is that in most applications of practical interest, the distribution P, which we actually need to evaluate the risk or the optimal risk, is hardly ever given to us. So in this talk, I'm going to assume that we're only given limited structural and statistical information about this distribution P. So first, I'm going to assume that I'm given a set capital Xi that is known to contain the support of P. And besides that, I'm going to assume that I have access to n independent samples from P. So that's all I know. Now, in this setting, it would be quite natural to use the training samples to estimate the distribution P hat, which I call the nominal distribution. And now we could just replace the unknown true distribution with this nominal distribution, and we could then formulate the nominal risk and the optimal nominal risk. And these would be quantities that, at least in principle, are accessible because they're constructed from observable data, unlike their true counterparts. Okay, so throughout the talk, I would like to work mainly with non-parametric and parametric models for the nominal distribution. So in the absence of any structural information, a very convenient choice is to work with the empirical distribution. So this is just a uniform distribution, discrete uniform distribution on the training samples. Now, on the other hand, if we do have some structural information, often it's convenient to work with elliptical distributions with that correspond to some density generator G. And once this density generator is fixed, then the distribution is actually uniquely determined by its mean vector and its covariance matrix. And these are the only quantities that need to be estimated from the data, which can be done conveniently with maximum likelihood estimation, for example. Okay. So now, even if you use the most sophisticated statistical tools, then the nominal distribution, P hat, our estimator, will invariably differ from the unknown true distribution. And if we use the nominal distribution in the risk evaluation and decision problems, then the estimation errors in the nominal distribution will be inherited by the risk and the optimal risk. And the very important question is now, so how sensitive is the risk with respect to misspecifications of the distribution? In order to answer that question, we first need to agree how we would like to measure estimation errors in the input distribution. And I will argue that the convenient way of doing this is by using the so-called Wasserstein metric, or the Wasserstein distance. The Wasserstein distance is studied in the theory of optimal transport. This is a field that was pioneered by Gaspard Monge in the 18th century, and where very important contributions have been made to by Leonid Kantorovich and Leonid Wasserstein. So there are different types of Wasserstein distances, parameterized by some p, which is a number between 1 and infinity. So the type P Wasserstein distance between two distributions Q and Q prime is defined in terms of an optimal transportation problem over all couplings of Q and Q prime. Now, if Q and Q prime are distributions on Rn, then coupling is just a distribution on R2n, whose marginals are Q and Q prime. So the optimal value of this transportation problem here can be interpreted as the minimum amount of money you will have to pay in order to transform one pile of dirt corresponding to the distribution Q to some other pile of dirt corresponding to the distribution Q prime, where the price you have to pay for shifting a unit mass from xi to xi prime is just the distance between xi and xi prime to the power p. So we measure the distances with some norm in the xi space, and we're free to choose the norm in principle, so that gives some degree of flexibility. Okay, so the Wasserstein distance is very convenient because it allows us actually to analyze how estimation errors in the input distribution are propagated to the risk. So to see this, let's look at an example. Let's assume that we're given a loss function that is Lipschitz continuous and has a Lipschitz modulus L. Let's also assume that we're given an estimator p hat, a nominal distribution, that is known to have a type 1 Wasserstein distance to the unknown true distribution of at most epsilon. So in some sense, we're saying that the estimation error is known to be bounded by epsilon. In this case, what can we say about the estimation error in the risk of the loss function L? Now, by actually using the celebrated Kantorowicz-Rubinstein theorem, we can estimate the risk, we can estimate the estimation error in the risk, or we can bound it by the Lipschitz modulus of the loss function multiplied by the epsilon. And very similar calculation can be carried out if we're looking at all admissible loss functions, and if all loss functions are jointly bounded above, have a Lipschitz modulus that is bounded above by a common L. So in this case, again, the optimal risk is bounded above by, the estimation error is bounded above by the Lipschitz modulus, or the common Lipschitz constant times epsilon. So this analysis gives us a rough understanding of how estimation errors in the input are propagated to the risk. In fact, they're at most amplified by the Lipschitz modulus of the involved loss functions. Yes?
Is it just an immediate result of the duality theorem?
Exactly, yes. So the optimal transportation problem has a dual reformulation, and strong duality holds almost always, and this is the Kantorowicz-Rubinstein theorem. And so the dual problem actually says that the Wasserstein distance can be expressed as the difference between the expected values under Q and Q prime of some test function, which is Lipschitz continuous with Lipschitz modulus 1, and then this difference is maximized over all such possible test functions. And now here, if we divide the loss function by L, then we get a test function of Lipschitz modulus 1, and we can apply it. Yeah. So this preliminary analysis suggests that if we would like to have low estimation errors in the risk, then we should try to find estimators that have a small Wasserstein distance to the unknown true distribution. Unfortunately, no estimator is perfect, and if we're given a finite set of samples, then there are fundamental performance limitations to estimators. I mean, there are things like Cramer-Rao bounds, and beyond a certain point, we just cannot improve the estimator further. Now, it turns out that once we've exhausted the possibilities of choosing a good estimator, we can actually still further improve the out-of-sample performance of our optimal decision, so the optimal loss function, actually by changing the optimization problem itself. And there are different ways to do that. The way that I would like to advocate in this talk is to robustify the risk evaluation and decision problems with respect to distributional uncertainty. So I would like to robustify them with respect to all distributions Q, under which our estimator has an estimation error that is at most epsilon, under some Wasserstein metric. So more specifically, I would like to define an ambiguity set. So that is a family of distributions, subset of the set of all possible distributions, and I define it as the set of all Q supported on the set Xi that have a Wasserstein type P distance from our estimator of at most epsilon. Of course, this can be seen as a ball, as a Wasserstein ball in the space of distributions, and it contains all distributions under which our estimator has an estimation error of at most epsilon. And the radius epsilon here can be viewed as the maximum estimation error against which we seek protection. So using this ambiguity set, we can now alter our risk evaluation and decision problems by taking a worst case view. So we can define worst case risk as the supremum of the ordinary risk over all distributions in the Wasserstein ball, and we can define the worst case optimal risk as the infimum of the worst case risk over all admissible loss functions. And of course, solving this worst case optimal this decision problem is a distributionally robust optimization problem. So it is a zero-sum game where the decision maker first picks a decision, a loss function, and then some fictitious adversary or nature chooses a distribution in the Wasserstein ball with the goal to inflict maximum damage to us. So by preparing for the worst, we hope that we will make good decisions that generalize well. So that's the idea. So, question?
So isn't comparing the risk for different losses kind of like comparing apples to oranges? Like you are minimizing with respect to different losses, like this risk and like the loss, like the risk for a different loss.
So maybe there is a misunderstanding. So you should think of this loss function as some function that you would like to say it's the cost, right? And it depends on some decision, but it also depends on uncertain parameters. So you think of this as L of x and xi, where minimizing here over L is actually minimizing over x.
Yeah.
Is that?
What does comparing like squared loss as opposed to mean like absolute loss?
So you're thinking about classification or regression, right? Where the loss function would be like the hinge loss, but then the hinge loss is evaluated at I mean, you have your hypothesis, which is some weight vector multiplied by a feature, and you multiply this by a label. So your weight vector W is actually the thing you're optimizing over. So what I'm referring to as the loss function here is actually this L of W times X times Xi. So I would minimize over the W here, okay? Okay, any other clarifying questions? Yeah.
So a related question. So which P do you choose? Because there would be interaction between the cost for the transport problem and the loss function of the problem that you are addressing.
So at this point, I only need to choose my estimator. And
no, I mean the Wasserstein P Wasserstein distance.
Ah, okay. Which one? Okay, yeah.
The question behind that is that there need to be an interaction between the cost for the transport problem and the loss function.
Actually, I do not know. That's my honest answer. What is the best choice of P? But for some problems, some P's are meaningless. So actually, if you use the type P Wasserstein distance, then you can actually move probability mass to the infinity if that mass decays as 1 over distance to the power P. And now if your loss function grows too fast, say quadratically, and you use a type 1 Wasserstein distance, then the worst case, this supremum will be infinity. So the kind of loss function you're using restricts the types of P's that you can use to get actually finite and therefore meaningful results in the first place. But, yeah.
So in this ambiguity set, if we increase P from 1, this becomes smaller.
Yes.
So it's like if we increase P, we can say that we are more conservative.
Yes. Yes. So the less you know, so P equals 1 is the most conservative choice, and actually most of the results I'm going to give you later on will be for P equals 1. So we're on the safe side in that respect. Okay. So since this is an optimization problem over an infinite dimensional space of distributions, and this is actually a zero-sum game, an infinite dimensional zero-sum game, we might expect that it's difficult to solve these problems exactly, and therefore I'm first going to give you 3 different bounds that should be more easy to evaluate. So the first thing I would like to do is I would propose, in the situation when we work with the discrete empirical distribution, I would like to propose a optimistic lower bound on the worst case risk. And this lower bound is actually obtained by reducing the Wasserstein ball to a subset that contains only perturbed empirical distributions, where I'm only allowed to move training samples around. So basically each training sample I can shift by an amount theta I, and I'm optimizing over all such possible discrete distributions. So this gives me a lower bound, and this is actually a convex optimization problem if my loss function happens to be concave. So in this case, we should expect that this is easy to evaluate. Okay. If we replace our the exact risk with this lower bound in the decision problem, then we actually solve a robust optimization problem where these thetas play the roles of the uncertain parameters. We can also get a conservative upper bound, maybe more interesting. Indeed, we can show, it's easy to show that the worst case risk is upper bounded by a sum of the nominal risk and something that looks like a regularization term, which is the radius of the Wasserstein ball multiplied by the Lipschitz modulus of our loss function. Okay. There is also a third conservative upper bound, which is a bit more complicated to construct and which applies only if we're working with the type 2 Wasserstein distance and if you use the Euclidean distance in the Xi space to measure transportation costs. So this third upper bound can be constructed by using a lower bound on the type 2 Wasserstein distance, an analytical lower bound on the type 2 Wasserstein distance between two distributions Q and Q prime, which depends only on the mean values and the covariance matrices of these two distributions. So of course this lower bound can always be evaluated easily, even if it is hard to evaluate the exact Wasserstein distance precisely. So this lower bound was first discovered by Gelbrich, and it has the note, and I'm going to denote it in the rest of the talk by DG, right? So it actually defines a metric on the space of mean covariance pairs. Interestingly, this lower bound is tight, and so it becomes an equality whenever Q and Q prime are two elliptical distributions of the same type. So if both are normal distributions or if both are T distributions, then this is exact. So I'm going to use this Gelbrich lower bound, this Gelbrich distance, to construct an upper bound on worst case risk. And this is a bit complicated. So first I'm going to introduce an uncertainty set in the space of mean covariance pairs, and I'm going to denote it by U epsilon. So you can think of this as a ball with respect to this Gelbrich metric on the mean covariance space, which is centered at the mean and the covariance matrix of the nominal distribution. So these are denoted by mu hat and sigma hat. Okay? Now, this uncertainty set can be used to construct an other ambiguity set. So to do that, I'm going to denote by T the projection that maps any distribution Q to its mean vector and its covariance matrix. And actually, this mapping, because of Gelbrich's theorem, will map any point, any distribution in the type 2 Wasserstein ball to some point in this mean covariance uncertainty set. So basically, the image of the Wasserstein ball under T is contained in this uncertainty set. And more notably, if the nominal distribution P hat is an elliptical distribution, then because in this case the Gelbrich bound becomes exact, one can show that this mapping is surjective. So in this case, the image of the Wasserstein ball under T is exactly equal to this uncertainty set. Okay? Yes? T just takes the distribution and calculates its mean value in this covariance matrix. Yeah. It's a nonlinear map, but it's yeah. Okay, so I'm going to use this T and this uncertainty set to define another ambiguity set, so another family of distributions that I'm going to call the Gelbrich hull, and I'm going to denote it by G epsilon. So I define it as the pre-image of the uncertainty set under this mean covariance projection T. So by definition, this means this Gelbrich hull contains any distribution whose mean vector and covariance matrix resides in the uncertainty set U epsilon. And it is actually an outer approximation of the Wasserstein ball. Indeed, if this Gelbrich hull contains any distribution, some distribution Q, then it will contain every other distribution that has the same mean vector and covariance matrix as Q. So it could actually be much, much larger than the Wasserstein ball. However, we can use it to construct now finally our upper bound on the worst case risk. So basically we can just replace in the definition of the worst case risk the Wasserstein ball with its Gelbrich hull, this outer approximation, and take worst case expectation over this larger set. So this gives us an upper bound. Okay? So we have developed 3 upper bounds. I will argue later that it's easy to compute them in interesting situations. Actually, this upper bound I'm going to refer to as the Gelbrich risk, and I'll just use the symbol R bar for it in the rest of the talk. Okay. So interestingly, all of these three bounds are tight. Yes?
Are these two bounds comparable from the empirical distribution and this one, the Gelbrich?
So actually, that will be the next part of my talk. So I'm going to show to you situations in which these bounds are tight and situations in which they can be efficiently computed. So maybe we postpone that question a bit until this we have seen this. Okay. So the main vehicle to derive tractable reformulations for the worst case risk evaluation problem is a strong duality theorem, which expresses the worst case risk, Wasserstein risk, as the optimal value of a univariate convex minimization problem, where the decision variable here is a scalar, which is essentially the dual variable of the Wasserstein constraint. And this optimization problem also involves this Moreau envelope of the loss function. So you can think of this, if you do convex analysis, you can think of this as being related to the informal convolution of the negative loss function and the pth power of the norm function. Okay? So this result was first derived in the just for p equals 1 and for discrete nominal distributions on finite dimensional spaces, but it was later significantly extended to arbitrary p's and to arbitrary nominal distributions, even on Polish spaces. So this is a very general result. This can be used to find exact tractable reformulations of the worst case risk evaluation problems in certain settings for certain loss functions. One example is when the loss function is piecewise concave. So that means when the loss function can be expressed as a pointwise maximum of finitely many concave functions. I would like to point out that this is a weak assumption, right? Many functions can be written as a pointwise maximum of concave functions. So this leads us to a first main result. So let us assume that the set psi containing the support is a convex set. The nominal distribution is the discrete empirical distribution, and the loss function is piecewise concave. Then we can reformulate exactly the worst case risk as the optimal value of this finite convex optimization problem. There's a question.
Yeah, I'm confused about this concave convex because I would expect the loss function to be convex, not concave.
So the loss function, we want it to be convex, ideally, in the decision variables. Now I've suppressed the decision variables. So if you think this depending on some x as well, then we would like it to be a saddle function that is convex in x. But typically, we would like it to be concave in the uncertainty. That turns out to be the...
So let's take the square loss, for example.
Yeah, wouldn't satisfy it.
Okay.
So that's not an example of this, right? The hinge loss would be okay.
The hinge loss
Yeah.
is okay.
Log loss is also not okay. Yeah.
So you require a small number of pieces?
Finite. Finite. Yeah.
Otherwise, concave, convex function.
The combination.
Yeah, if infinitely many, of course, I can take the envelope. Yeah, and yeah. There are also results for convex. I will come to that later. Yeah.
So there's no assumption of Lipschitzness, I mean, the function L is...
The only thing we assume is what I didn't say, but it is here on the slide. There need to be proper concave and upper semi-continuous.
But at the end of the day, because you want to like bound the estimation error, so you show that it's less than epsilon L, the Lipschitz. But if L is not Lipschitz,
Ah, okay. Actually, good point. So, so the function doesn't have to be Lipschitz. And of course, if this is a concave function becomes very steep, then it will not be Lipschitz, but it is calm in some sense from above, right? So it cannot grow more than linearly. No concave function can grow more than linearly, and if you take a finite pointwise maximum, then this will also grow at most linearly if we move psi to infinity. And that will mean that the type 1 Wasserstein distance doesn't allow us to move mass in a direction so that the expectation goes to infinity. So this will be finite. Yeah, that's a good point. Okay? So we have this exact reformulation. This is an optimization problem that involves some auxiliary decision variables that we just picked up by dualizing the problem, and actually from dualizing the Moreau envelope that I showed you before. It also involves some new constants like the Q, which is actually the normal Q that corresponds to the P subject to this normal PQ conjugacy relation. And I should point out that this problem is indeed convex. So the last constraint group involves the convex conjugate of the negative component function Lj. It involves the support function of the set xi, and it involves the perspective function of the dual norm to the power q, and all of these are convex functions. Okay, so this is indeed convex optimization problem. The size of this problem grows linearly with the number of training samples, and it grows linearly with the number of concave components. So there is hope that under reasonable situations we can solve this efficiently. Okay.
So is the size the product of two sizes?
By size, I just mean the number of decision variables and number of constraints at this point.
Yeah,
Of course.
Is the size of this program the product of the size of the training set and the number of pieces? Or is it just like adding?
Yes, because we have variables Vij, I indices. Yeah. These are the training samples, and J are the pieces. Yeah.
Right.
So this is a minimization problem, and that is useful because I had a minimax problem at the beginning. I reformulated the inner problem as a minimization problem, so I can join this minimization problem with the outer minimization of the loss functions, which will give me an overall minimization problem. And in interesting situations, this overall problem will also be then a convex problem that we can solve. So this is nice. It's still instructive to actually dualize this convex program, because this will give us information about the worst case distribution. So if I dualize this problem, I obtain this convex maximization problem shown here. And I would like to point out in the special case when our loss function is concave, so there's only one piece, the capital J is 1, then this exact reformulation reduces exactly to the robust lower bound that I showed you first. So this shows that the robust lower bound is actually exact when we have a loss function that is concave in the uncertainty. One can show that this problem is always solvable, and if it's solvable, then we can extract from it a distribution that attains the worst case in the Wasserstein risk evaluation problem. And if the worst case distribution may not always be attained, but this problem is always solvable. And if there is no worst case distribution, we can use the solution of this problem to construct a sequence of distributions, discrete distributions, that asymptotically attain the worst case. So here's a summary. If the loss function is piecewise concave, the nominal distribution is the empirical one, then the worst case risk can be computed by convex optimization for any p between 1 and infinity, and this generalizes the earlier result for p equals 1. So the dual convex optimization problem showed us that if the loss function is concave and the nominal distribution is empirical, then the robust lower bound is actually exact. And the dual convex program provides a finite reduction of the worst case risk problem. It is always solvable, and it can be used to find the worst case distribution if it exists, or it can be used to find a sequence of distributions that are asymptotically extremal if such a distribution does not exist. Yeah?
Quick question. So the worst case distribution is a discrete distribution with n samples?
No, it is discrete, but it... So actually, it doesn't follow from this, but one can prove there is always a worst case distribution with n plus 1 samples. Okay? Yeah.
Is it always?
What would follow from that? You see the alpha ij's are sort of the probabilities of the worst case distribution that we obtain, and the samples, so the discretization points are the locations of the original training samples plus these fractions, right? These are vectors, but there is one for each j in principle, and these are the probabilities. And in principle, you could have now as many as number of samples times number of concave pieces. So that's all what this theorem gives us, right?
Is this only true under Wasserstein ball or true under general convex constraint on the problem?
So it's a bit hidden here. Actually, to derive this, what we do is so the worst case risk evaluation problem can be reformulated as a linear, can be seen as a linear program over distributions. It can actually be seen as a moment, it can be reformulated as a moment problem. And for moment problems, we know that the extremal distributions, if they exist, are always discrete. And this is related to that. So this is a special case of a more general situation. Yes?
Maybe just a quick question, but is it possible to see that this worst case distribution is always going to lie close to the boundary of this epsilon ball?
So if the radius is small, of course, you should expect that this will be on the boundary of the ball. But if you make the radius very, very big, and your loss function has somewhere a local maximum, right, say concave, right, then nature will try to push probability mass to the maximum of the loss function. And if the transportation budget, so the radius epsilon of the ball, is big enough, it will actually be able to move all the probability mass to the local maximum. Then this reduces actually to the worst case, not the worst case expectation, the absolute worst case of the loss. And that can happen, and then the constraint wouldn't be binding anymore. Yeah. Okay. So this was our conservative upper bound. And the second theorem is that if we have no support constraints, so Xi is the whole space, and the loss function is convex, then the type 1 worst case risk is equal to the Lipschitz regularized nominal risk. Okay, so this first conservative upper bound is exact in this setting. I'm not going to prove this, but I'm going to give you some intuition. So let's look at a situation where Xi is just a scalar random variable, and we have 3 training samples that have this probability 1/3 each. And we're going to look at the Wasserstein ball around this nominal distribution of radius epsilon 0.7, say. Okay? So let's look at the convex loss function. In this case, I chose a piecewise linear one, which looks like this. So nature will now try to modify this nominal distribution, to reshape it at a transportation budget of at most epsilon, with the goal to make the expectation of this loss function as large as possible. It turns out that in this example, what we should do is we should actually move a decreasing portion of the third training sample infinitely far to the right, which is the direction in which this loss function grows steepest, right? So actually, here is a video of what happens. In the upper panel, I show you how the perturbed empirical distribution looks like, where a small portion of the probability goes to infinity. And on the lower panel, I show you the expected value of the loss function under the perturbed distribution as a function of the shift theta. And what we see is that this expectation grows and actually converges asymptotically to the Lipschitz regularized nominal risk, which you know to be an upper bound. And this shows that in this example, the upper bound is tight, not attained, right? But it's asymptotically attained by this sequence of distributions that sends a small probability mass to infinity to the left, to the right.
So the proportion, the further away you get, can you run the movie again?
Yeah.
I see.
So I cannot, up to here I can move the whole probability mass, but then my budget epsilon is not enough, and I can only move a portion, right? And then this needs to decay as 1 over theta, basically, because I use the type 1 Wasserstein distance. Yeah. Okay. So again, if the loss function is Lipschitz, we have no support constraints, and P is 1, then the worst case risk coincides with the Lipschitz regularized nominal risk. One can show that no distribution ever attains the worst case risk, except in very naive, trivial settings where the loss function is linear. However, it is asymptotically attained by moving a decreasing probability mass to infinity in the direction of steepest descent. I should point out that computing the Lipschitz regularized nominal risk looks simple, but it's not tractable. So even for very simple convex loss functions, computing the Lipschitz modulus of these functions is NP hard. So this result is only useful if we look at loss functions where it's easy to compute the Lipschitz modulus, and I'm going to give you some examples later on. Yeah?
So what happens if the data lies in a hypercube, for example?
Yes. So you would like to have a, you say you know that it's in a hypercube, and I'm going to have,
information about.
If I know it's in a hypercube, I'm going to define the set capital Xi as this hypercube. Yeah. Then actually, I cannot say anything about if the loss function is convex and not piecewise linear. If it's piecewise linear and convex, I can write it as a pointwise maximum of linear functions. So the first result applies, and there I could handle the support. But if I use log loss or quadratic loss and have a support, then this problem is hard. Cannot do it. Okay, so let's now turn to the Gelbrich bound, the third one. You remember that we had this mean covariance protection, which mapped the type 2 Wasserstein ball to this mean covariance uncertainty set, and the Gelbrich hull was defined as the pre-image of this uncertainty set. Now, this construction actually means that the Gelbrich hull can be written as a union of Chebyshev ambiguity sets. So a Chebyshev ambiguity set is a family of distributions, all distributions that share the same mean value and the same covariance matrix. Okay? So if I take the union of these Chebyshev ambiguity sets over all mean covariance pairs in the uncertainty set U epsilon, I recover exactly the Gelbrich hull. Now this decomposition into Chebyshev ambiguity sets can be used to reformulate the Gelbrich risk, so the worst case risk over the Gelbrich hull, as a nested optimization problem, where the inner maximization evaluates the Chebyshev risk, so the worst case expectation over the Chebyshev ambiguity set for a fixed mean covariance pair, and the outer maximization evaluates the worst Chebyshev risk over all mean covariance pairs in the uncertainty set U epsilon. So this is like a two-layer distribution robust optimization problem. The inner one accounts for shape uncertainty, the outer one for moment uncertainty. Now this decomposition can be used to derive tractable reformulations in different settings. One setting where it works is when the loss function is piecewise quadratic. So it could be written as a pointwise maximum of finitely many quadratic functions that could be convex, concave, or indefinite. It doesn't matter. So in this case, if you have no support constraints, the loss function is piecewise quadratic, then the Gelbrich risk can be reformulated exactly as the optimal value, as this tractable semi-definite minimization problem, or its strong dual maximization problem shown here. And as before, the minimization problem is useful because it can be combined with the outer minimization over the loss functions to obtain one single optimization problem. Whereas the maximization problem is useful because it will give us information about the worst case distribution that should attain the Gelbrich risk if it exists. So here's a brief summary. The Gelbrich risk bounds the Wasserstein risk because I inflated the uncertainty set. So therefore it inherits all statistical guarantees that the Wasserstein risk might offer you. It can be computed efficiently via convex optimization. It also induces this uncertainty set U epsilon for the mean covariance pairs. And that leads to an outer robust program, which is actually convex for any loss function. And that is something that is a bit remarkable if you know the literature on distribution robust optimization, because people have tried to come up with an outer layer of robustification for moment uncertainty in other settings, and this has never quite worked. Only for special cases, they have found uncertainty sets driven by tractability that worked. Now, this uncertainty set is actually very natural, and it will give a convex outer maximization problem for any loss function. So that's quite nice. So maybe most importantly, and I can't show that now, but the Gelbrich bound is exact if the loss function is quadratic, a single quadratic, right? Concave, convex, or indefinite, and the nominal distribution is elliptical. So this is a restricted setting, but it shows that the Gelbrich bound is tight. And this has interesting applications that I hopefully can show you later. The worst case distribution is available in closed form in the same setting. So if we have a quadratic loss function and an elliptical nominal distribution, we can show that it's hard to compute. The worst case distribution for the Gelbrich risk is hard to compute in general if the loss function is piecewise quadratic. So this is NP-hard. OK. So let me show you some examples of this in the context of machine learning. Of course, you can think of, you can use these techniques in many, many different other areas. Let's look first at classification, where we would like to predict a binary output y from some continuous input x. And of course, yeah, the goal is to predict y from x. So we denote by xi the combination of inputs and outputs. And of course, this will follow some distribution p, which we don't know. Now, the ideal classifier would be the one that predicts that an image shows a cat if the conditional probability of the output being 1, conditional on the input is more than 50%, and will predict a dog otherwise. This ideal predictor is, of course, not available to us because we do not know the distribution p, so it's not accessible. And the only thing we have is we only have training samples from the distribution p, annotated, labeled images. So in this case, what we usually do is we try to find a linear predictor. So we try to predict the output corresponding to an input x as the sign of W transpose x, where W is some weight vector that we estimate in some way from the training samples. So the prediction is correct if the product of the actual label, the actual output multiplied by W transpose x is larger than 0, and it's incorrect otherwise. So the prediction error can therefore conveniently be measured by some convex loss function that is small if the prediction is correct, so small if this product is positive, and large if the prediction is incorrect, meaning if this product is negative. So the typical examples, we already discussed them, are the hinge loss, which is used in support vector machines, the smooth hinge loss, which irons out the kink at 1, or the log loss, which is used in logistic regression. Now, the naive approach would be first to try to find a W that minimizes the empirical prediction loss. But if you have few training samples, then this problem is prone to overfitting, and we should regularize it. Now, instead of regularizing it in the usual way, what I propose is to actually robustify it against distributional ambiguity. So to replace this nominal expectation, the nominal risk, by a worst-case risk over a type 1 Wasserstein ball. Okay, sorry. Now, in order to clearly define what I mean, I have to define the Wasserstein distance I'm working with. I work with a type 1 Wasserstein distance in this case, because all these loss functions are Lipschitz continuous. And I need to specify a norm, the transportation cost on the input-output space. What I'm going to use, I'm going to use an additively separable transportation cost. So the norm of xi should be some norm of x plus kappa over 2 times the absolute value of y. Now this kappa parameter here is positive, and you should think of it as the confidence we have in the labels. So if you're nature and you try to move around input-output pairs, then you can think of the kappa actually as the cost that nature has to pay to flip a label. If the kappa is large, it means nature is expensive for nature to change the labels, so that means that we believe that the labels are actually correct. So this is our distributional bus classification problem. Now we have this theorem here. We can show that if this trust in the label goes to infinity, so we have infinite trust, we believe that the labels are correct, and if p is 1, then we can prove that this robust classification problem is equivalent to the problem that minimizes the Lipschitz regularized nominal risk. So this is just a classical regularization approach where we minimize the empirical loss plus some regularization term, and the regularization function is just a dual norm of W, where this is the dual of the norm that measures distances in the input space, and the regularization weight is just the product of the Wasserstein radius and the Lipschitz modulus of the loss function. So this gives a new probabilistic or robustness interpretation of regularization schemes that have been used routinely in statistics and machine learning. So this interpretation holds if you have infinite trust in the labels. Okay. So very similar story applies to regression. So here we'd like to predict a continuous output instead of a categorical output. And same situation as before. So if we knew the joint input-output distribution P, then the ideal predictor would be the conditional expectation of the output given the input. So this is the one that attains the minimum mean square error. But of course, it's not available because the P is not given to us. Instead, we're just given samples. And in this case, again, the usual approach is to look for affine predictors, which predict the output as some affine function W transpose X. So the prediction error is just the difference between the predicted output and the true output, can be quantified by a loss function L, which is usually chosen to be convex, 0 if the argument, the error is small, and which is large if the argument differs from 0 in either direction. So the typical examples are, of course, the square loss, which is used in least squares regression, the Huber loss, which gives less weight to the outliers, the delta insensitive loss, which is used in support vector regression, or the pinball loss, which is used in quantile regression. So again, we have a nominal risk minimization problem, and we regularize it by formulating the distributionally robust version of it. Here we use an arbitrary type P Wasserstein ball for the moment. Again, I need to specify how I'm going to measure transportation costs in the input-output space. And I'm going to use the same norm as before, which is additively separable with some norm on the input space plus kappa over 2 times the absolute value of the output. Similarly to before, we can prove that if we have, actually in this case, kappa reflects the relative weight of the outputs with respect to the inputs. So again, if kappa is infinity, and we believe that the outputs have no uncertainty, and if p is 1, then again, this distributional robust regression model reduces to the problem that minimizes the empirical loss plus the same regularization term as before. Now, if we solve a least squares regression problem, so we use the squared loss, then we actually need to work with the type 2 Wasserstein distance to get a finite result. So let's do that. At the same time, let's again set kappa to infinity, so infinite trust in the outputs, no output uncertainty. In this case, one can prove that this distribution robust problem is equivalent to this problem, which minimizes some combination of the square root of the empirical risk and this regularization term here. So now if we use the infinity norm to measure transportation costs in the input space, then this is actually the one norm. And in this case, this problem is equivalent to the generalized lasso estimation problem. So this gives this a distribution robust interpretation. OK. I should point out that if kappa is not infinity, then we still get convex optimization problems that are tractable theoretically. But these cannot be interpreted as classical regularized problems. So we get, in some sense, new regularization methods with two hyperparameters. The epsilon, which is the estimation error in the input distribution, and the kappa, which is the trust in the outputs. And we have to use, for example, cross-validation to tune both of those. OK. So as a third example, so these were non-parametric machine learning methods. I would like to look at the parametric setting where we are given n training samples again from some normal distribution with an unknown mean vector and covariance matrix. And I would just like to estimate these two parameters from IID data. And I'm interested particularly in the setting where the dimension m of this random vector is extremely large. So I would like to argue first, actually, that the covariance matrix is an important quantity for many problems in science, engineering, and economics. However, the inverse of the covariance matrix, the precision matrix, is a quantity that often appears in the output. So here are some examples. In linear discriminant analysis, for instance, you need the covariance matrix of the features as an input. The output is a maximum likelihood estimator, which depends on the precision matrix, or the inverse covariance matrix of the features. In the Markowitz portfolio analysis, you minimize the variance of the portfolio return, which depends on the covariance matrix of the asset returns. That's the input. The output is an optimal portfolio, which is a function of the inverse covariance matrix. Also, in the optimal fingerprint method in climate change detection, you need the covariance matrix of the internal climate variability as an input, and the output is a climate change signal that, again, depends on the precision matrix. So if you agree that outputs are more important than inputs, then we should agree that it's probably more important to estimate the precision matrix, X, than the covariance matrix itself. OK, so let's try to do that. So first very naive approach is just to estimate the mean and the covariance matrix as the empirical mean and the empirical covariance matrix, which are just the actual mean and covariance matrix of the empirical distribution that places mass 1 over n on each training sample. So if we construct these estimators, then we can try to construct an estimator from the precision matrix by just inverting this sigma hat here. So from now on, mu hat and sigma hat are my empirical mean and covariance matrix. Unfortunately, in the high-dimensional regime, where the dimension of Xi is much larger than the number of, or just larger than the number of training samples, this empirical covariance matrix is not invertible because it's just a sum of n rank 1 matrices. If m, the size of the matrix, is larger than n, I cannot never invert it. So I don't get a precision matrix estimator. So let's try something else, because we know that the data comes from a normal distribution. Let's try to use maximum likelihood estimation. So the maximum likelihood problem is equivalent to a convex minimization problem over all candidate mean vectors and candidate precision matrix estimators X. And the objective is to minimize some of the negative log determinant of X and some term that can be interpreted as the inner product of our estimator, of our candidate estimator X and the empirical covariance matrix. So this problem, in fact, can be solved analytically, and that's very nice. However, the problem is unbounded if the dimension of the data exceeds the number of samples. So in this case, again, we have no estimator that we can use. In the other case, when the dimension is smaller than the number of samples, the optimal solution of this problem is just the sample covariance matrix and the inverse sample, the sample mean vector and the inverse sample covariance matrix. So we actually haven't gained anything, right? However, now we observe that the second term here is actually just an empirical expectation of some quadratic function of the data. And of course, we will overfit if we have few data points here. And so let's just try to robustify this term here. So let's replace this empirical expectation by a worst case expectation over a type 2 Wasserstein ball. I work with a type 2 here because the loss function is quadratic. So as the nominal distribution here, I argue that it's reasonable to choose the normal distribution that has a mean and a covariance matrix that are equal to the sample mean and the sample covariance matrix. This is reasonable because I know that my data, I assume I know my data is normal. And moreover, if I set the radius epsilon to 0, then with this choice, this problem just reduces exactly to the normal maximum likelihood estimation problem from the previous slide. So by choosing an epsilon that is strictly positive, we actually have a robust maximum likelihood estimation problem in this way, quite naturally. So this problem has a lot of structure, and actually we can solve it in closed form. So let me show you the closed form solution in this theorem here. So this only if the epsilon is strictly positive. And what we need here is the spectral decomposition of the sample covariance matrix. So the lambda i's are the eigenvalues, large or equal to 0, and the vi's are the orthonormal eigenvectors. So we can prove that the optimal solution of the robust maximum likelihood estimation error problem is for the mean, just the sample mean, not very exciting. But for the precision matrix, the optimal estimator is a matrix that looks like this. So this is the spectral decomposition. It has the same eigenvectors as a sample covariance matrix, but it has different eigenvalues. The eigenvalues can be seen as nonlinear transformations of the sample eigenvalues given by this formula. This formula also depends on one scalar parameter gamma star, which is the only quantity we have to compute numerically, which is the solution of this algebraic equation down here. This equation can be solved conveniently with bisection, for example. So because the eigenvalues of our estimator are just nonlinear transformations of the sample eigenvalues, we can think of this estimator as a nonlinear shrinkage estimator. So this shows that, yeah, the robustification results in a shrinkage estimator, and shrinkage can be seen as a form of robustification as well.
Are we supposed to see that this is actually shrinkage? I don't see it, but...
You need to plot it. You don't see it, no. Actually, it's anyway, here we look at the precision matrix, so that the lambda I is the eigenvalue of the sample covariance matrix, and here we look at these are the eigenvalues of the inverse. So yeah, but you can prove it, and you can plot it, but I don't expect you to see it from this side. My apologies. Yeah. So since both the sample covariance matrix and our estimator share the same eigenvalues, it means that they commute. And this implies that our estimator is rotation equivariant. So that means that the estimator applied to the rotated data is equivalent to the rotated estimator of the original data. And according to statisticians, that is a desirable property for estimators, for covariance matrix estimators, if you don't have any prior structural information. One can also prove that if epsilon is positive, all the eigenvalues we compute in this way are positive, so our matrix is always invertible. And it's extremely easy to compute. The most computationally heavy step is to compute the spectral decomposition of the sample covariance matrix. So there's a number of nice properties of this estimator that are sort of listed on this slide. So the estimator exists for any m and n, even if the dimension of the data is much larger than the number of samples. The estimator is rotation equivariant. And one can also show that it preserves the order of the eigenvalues of sigma hat. So it doesn't, eigenvalues don't, there's no intersection, they don't cross each other. Which is intuitively appealing is that if you increase the radius of the Wasserstein ball and you make the problem more robust, you can show that the condition number of the estimator improves and it monotonically decreases towards 1. The complexity of computing the estimator is the same as the spectral decomposition of the sample covariance matrix. One can also show that this estimator offers out-of-sample guarantees on the Stein's loss, so that's like a distance measure to the unknown true covariance matrix. And all of these properties, actually, they are not imposed ad hoc, but they sort of naturally follow from this, I would argue, somewhat natural, robust formulation of the maximum likelihood estimation problem. In numerical tests, we've seen that the estimator has nice properties. So its performance is similar to that of a graphical lasso estimator. But of course, at the same computational cost as just a linear shrinkage estimator, it's very cheap to evaluate this one. The graphical lasso is much harder to evaluate because you actually need to solve a real semi-definite program, no analytical solution. Okay. Yeah?
And I assume the linear shrinkage estimate is not going to perform as well as this one.
So this is just, we cannot prove that, but we looked at a number of examples and we've seen that, yeah, the linear shrinkage estimator didn't do as well as the other two, but in terms of computation time, this estimator and the linear shrinkage estimator both require the spectral decomposition. Yeah.
So similar to other cases, is there an explicit regularization that gives you the same solution as this shrinkage kind of?
Well, I would argue in some sense the regularization is this thing, right? So it's a robustification, and that results in the shrinkage. I'm not sure what else I can. Yeah. So actually, the graphical lasso is basically obtained by adding a one regularization term to this whole thing, and then you can also prove that when the regularization weight is positive, this is always a solution. The disadvantage is that you have to solve a full-blown SDP in this case, so you cannot solve it analytically. So this is the attractiveness of this approach. Yeah.
Epsilon tends to 0 and is still positive. Does it tend to the pseudo-inverse of the?
Good question. I believe so, but I can't say for sure. Yeah. Okay. I think in the interest of time, unfortunately, I'm going to skip the last part, which is the one that actually relates a bit to control. Here is about to estimating some signal from a noisy observation. And this is sort of a problem that we would have to do in Kalman filtering. And so we just assume that the distribution of the joint distribution of the signal and the observation follows a distribution P that we don't know, but we believe that it's close to some elliptical distribution P hat. And then we can formulate a distribution robust mean square error estimation problem like this, where we basically try to find an estimator, psi, that's just a measurable function that maps observations to predictions, that minimizes the worst case mean square error, basically, right? And this is an infinite dimensional problem. So we optimize over functions here, and here we optimize over distributions. So an infinite dimensional zero-sum game. If the nominal distribution of this type 2 Wasserstein ball is elliptical, we can prove that this problem has an SDP reformulation, an exact SDP reformulation, which is this one here. And we can prove that the optimal estimator can be constructed from the solution of this nonlinear SDP and is linear. Okay? So even though we optimize over all possible measurable functions, that's a setting where an adaptive distribution robust problem has a linear optimal solution. So it's a case where linear decision rules, in the language of robust optimization, happen to be optimal. And this problem could be reformulated by using Schur complements as an exact, as a simple linear SDP, but this would be a very large one and would be difficult to solve. So what we actually developed as well is a Frank-Wolf algorithm to solve the nonlinear problem directly. And this algorithm has two nice properties. The first one is that it converges linearly. So that means we don't need many iterations. And the second one is that in each iteration, we need to find a direction, and we need to we solve a linearized version of the problem. And actually, this oracle subproblem has a closed form solution, which only requires some numerical solution of some algebraic univariate equation. So that means the complexity of one iteration is also very, one iteration is also very cheap. So this can be solved very quickly. Okay, so that's the end. Sorry that I had to rush through this. The summary is, I guess, that Wasserstein DRO machine learning models are interesting for a various number of reasons. First, they explain commonly used regularization terms. They give them a distribution robust or robustness interpretation. They can explain the benefits of some shrinkage estimators, as we've seen for the inverse covariance matrix. They can motivate new regularization schemes. So in the case of regression and classification, if we do not set the kappa parameter to infinity, we get new regularized problems. Very often we get reformulations that are equivalent to efficiently solvable convex programs. Sometimes they're solvable in quasi-closed form. The only thing that needs to be numerically would be a bisection. And in some settings, we have very efficient Frank-Wolf algorithms, first-order methods that solve them. Okay, so I guess I'll stop here. Here's a list of papers on which the talk is based. The first one is a tutorial paper that pretty much covers everything that I've discussed. And if you're interested in some of the proofs, then you have to go to look at the other papers. Thank you very much for your attention.